if I combine the explanation here on how to prepare the quantum state for, like, how to encode the frequencies, no, how to encode the samples, sorry, and to prepare for the QFT, if I combine this with the quantum programming book from O'Reilly, it just, I mean, first of all, and again, this is just, I'm not gonna go through those pages because I think it's not fair to show this content. You should really buy the book if you really want to read through this, and it's actually, I think, one of the best QFT explanations. It still doesn't go down to the level that I would like to, but at least the encoding of the signal, that's what kind of the way it's explained, that's how it ticked me, right? And I have to accept this is maybe the first time where I see a downside on the way this is represented here, but it's because the way this is encoded is basically by encoding your samples, uh, encoding the signal in the phase, right? In a way that, if you see here, in a way that, so here we've got the phase pointing at like the top, and then here we got it again pointing at the top, right? So basically it means it's done a full round. So that's like, that would be the equivalent of like a sort of one full, I don't know if it's like, yeah, I guess that's, so one full cycle. That would be the idea. So exactly. So I think this is the way it is encoded. So this is the way it is encoded. I think there's another example here. Exactly. So here basically they say the output is 2 because it and this is the frequency, right? And this is exactly what is explained in David's blog as well. Trying to make a whole sort of like a concept out of all these, taking a look at different guides. Exactly. So all this is doing, if I understand this well, is finding you, the outcome is the pattern, right? It's telling you the pattern, which is, I guess, what makes this useful for other algorithms. So it's less about here really the signals and whatnot, but it's about finding a pattern in your phase. And I think that's what makes it useful for Shor's algorithm. Give me a second, excuse me. Okay, now better sound probably. So I think that's what makes it useful for Shor's algorithm. But I'm not so sure if that's really the case or not. But it's really about finding the pattern in the phase. Now I'm not really. I think the one thing that I still don't understand is how is that pattern being constructed out of this, right? So this is the example. This is the example that we're given in the IBM Q experience, where they say the result of this should be 1, so 001. Yeah. But I'd like to play with with another pattern. I don't know if it makes sense if I do something like this, and then I do something like this. And if I apply the now the gates as they are written there. So it's basically pi divided by 2. Here we gotta do something like this. Pi divided by 4, and then another one, and then pi divided by 2, and then another Hadamard. What I should do is I should have another, maybe I can use this one here. Okay, yeah, I should use that. So I can just play with the input separately. Because if I go back to this input, then it tells me it's 1, right? But I mean, it doesn't have to be always perfect, right? That's also what they say in the book here is, I mean, if you're, that's the idea, right? If your wave is not pure, then you're gonna have like the composition of the different frequencies. So if that, assuming that is correct, if I just mess up with these numbers, and I do this as I was doing before, right? So this would literally mean that that this wave is composed. My input is composed of. So the pattern is like it's almost 90%. It's not 90%. It's 82%. So it's like 82% of frequency 1, then of a wave of frequency 3, of frequency 5, and of frequency 7, right? So all of them like added up with these weights. Exactly. That's basically what the pattern is telling us. What the QFT is telling us. But I'm not. I one thing that I would like to do is I could just now say done. We get it. I would like to understand a bit more the way this functions internally, maybe without really diving into the maths necessarily. Trying to think of a better example. Maybe there's another way. The other thing is you probably cannot encode your samples directly. So if you have to do a little bit of magic before, I think, because if this is what you're getting, if these are the samples you're getting, if these are the samples you're getting, right? Maybe you can encode them directly. Maybe you can encode them directly. That'll be interesting. That'll be interesting to play with. It's a pretty big example in this case because there's like 8 samples. But what if we take 4 samples? So, and I basically add 1 more qubit to the mix, qubit 4, and we add another U1, and now I take 4 samples directly from here. So 021, 083. Now I take 021. I'm gonna take so 078, is 0.78, 0.78. Then I'm gonna take 0.21 again, 0.21 again, and then I'm gonna take minus 121, right? Minus 121. Minus 121. So this is my input. Let's just start from scratch. This is my input. Okay, and I see, that's pretty nice, because here I do see graphically sort of a pattern. Nice. Which actually, I have to take back probably what I said about this representation not being good enough. I mean, I see definitely, like, we definitely see visually a pattern here of colors, right? So, so what is by the way, do we have the answer of this here so we can check? QFT. Do we have the answer or not? Equation 6. QFT coefficients as follows. Come on. Because I can also look for another example, maybe. Small DFT example. DFT examples. DFT examples. Bleh. Something nice. I mean, I don't know. Let's give it a try with this first. Let's see what happens. Let's follow the algorithm as described there. So, and kind of see what happens, because what I see here is when we are adding the Haramarts, right? When we're adding the Haramarts, so we're kind of losing some of those uncertainties here. Then I'll apply that, and I'm assuming it's always the following pattern. So it's pi divided by 2. Then the next one is pi divided by 4, but like this. The next one is pi divided by 8, but this. Exactly. So when I'm adding this, the issue is when I'm adding these things here, I don't necessarily see a change in here, which kind of bothers me a little bit. But I guess it's because you're changing just the phase. Right? Does anything change? Pi divided by 8? Oh yeah, actually something changes. Okay. Yeah, I mean, Okay, the things are moved around. So pi divided by 8 and this here. And now we kind of repeat by doing like that and having I don't know if I can just copy the, if I can copy the the controls. So I'm gonna copy, I think this is exactly those controls here, but they are like that exactly. And now we're gonna do a Hadamard here, and now we're gonna copy. Now you're just gonna have this, and now we're gonna have another Hadamard here. Yeah. So this is basically the result. If I go to the measurement probabilities, this is the result. So it's mostly composed of. Doesn't mean frequency 0, man. But I don't know if that's the correct result or not. I have to find an example that helps me understand a bit more what's going on. But if I'm using for some reason I don't know why, maybe I should change the signs here. Does this change the result at all? Because in the in the Q experience guide, they're using they're doing a minus, but I think that doesn't really change anything. No. So let's put it back. Let's put it back to what it was. It's probably way easier if I just touch it here. Okay, so I'm looking for another example, but I think I got the encoding right. So the encoding is basically, and let me remove all this. I'll copy paste it somewhere else. Okay, so the encoding basically is doing that on the face here. I mean, I guess there are other ways you can do that. In the book, they also say you can encode it in the amplitude, but it's probably way more complicated to do. And then the result you get is a little bit different to read. Yeah, so. What I could also try is these. So this is basically, I would say, sort of a square signal, right? It's just because I think it makes it easier for me to see here and to prepare. But the idea is, you see, right? So it's like for 4 elements, it's always positive and then negative, positive, negative, like +1, -1. So literally, this is something like this, like this, like this, like this, like that, like that, like that, like that. So you want to know how is it composed? Like, what is that composed of? And so if I do this here and I add the Z here, so this is the result of, yeah, so 4 and what is 2 decimal? What is that? It's like 12 or something. Yeah, 12. So 4 and 12. Okay. So this means that this is what this is made of, this signal. Okay. 50% 4, 50% 12. So I'm not
I guess the way you would encode the trick is how you really encode the. So the trick is how you really encode that, but the intuitively you do that in the phases, and that's what's important, right? So, but you understand the concept, right? So this is the because you can encode whatever you want by just having those rotations that we talked about here, and then you get basically what would that be? What if I do minus? I mean, I guess I could play with this for ages. Um, okay, so now that we are completely, I think I can say I know how to I know how to encode the inputs. I mean, I guess it depends on the concrete on the concrete problem. Um, I guess I don't know if you can always put directly the samples or not. But let's say that it's basically you encode it in the phases, but it's still the so the magic here is what I'm gonna do now. I'm gonna tackle in the last video is try to understand this magic. To me, it seems like, and maybe if we go back to this case of the square, like this no here. So if you go step by step, if we go step by step, it'll be easier if I remove stuff in here. So can I comment that? Look at this. Whoop. Good. Let me add that here. I didn't know I could just comment. Just makes things so much easier. So what is the Hadamard? Is the Hadamard? So that's the Hadamard that we cannot it just be here? Give me a second. So it's the problem if I put it here is the same right now. So I wanna comment all this stuff so I can. So this is the state we're prepared. Good. So now we add the Hadamard, and basically what's happening here is, because here it's easy to see because it's a plus. Okay, so it's probably easier to see here because it's really the extremes, right? So it's like +1 -1. So when you add the Hadamard, you're basically so you're getting rid of half of those. I don't know if it makes sense to take a look at each of the rotations. Probably. So you add the first rotation, right? Here, cannot know easily what happened because I cannot look at this. That visualization makes it difficult. That makes it difficult. I have intuitively the impression it's kind of collecting all the stuff. It's like rotating. It's like folding. I don't know why I call it folding. It just I have this impression, right, that it's just doing. Um, because in this particular case, once we've done the Hadamard here, we go back to 0 for that particular qubit. So that qubit is really 0. So here really nothing happens, but but here in this case, here we're still in a superposition just in that qubit. So when we do the control Z on pi divided by 2, so 90 degrees, we're moving the phase of what? Of this, of this, of this, of this. So you're kind of moving the phase because without that, without that, without that, we've got like 0.35, 0.35, minus 0.35, minus 0.35. And if I okay, but in this case nothing happens, of course, because it's a 0. Stupid. Okay. But now here, yes, and actually in this first case nothing happens completely. For that particular example, right? In the first iteration there's nothing literally because that's 0. Okay. So we just got rid of like half of those, and then when I apply another Hadamard here, then we're getting rid of even more of them. So they're like 50. So 0.5 minus 0.5, etc., etc., etc. Now qubit 2, it's also 0 all the time. qubit 2, qubit 1, sorry. In this particular cases. So this literally means that this is also not going to do anything. Now maybe here it's where it's interesting, because this is where we've encoded like because here we've got like we've changed the phase. So now we're going to add a Hadamard. Now we're going to go to 1. So we're not going to go, so this qubit goes to 1. It doesn't go to 0 in this case. Yeah. So you've got 0, 0.7, 0.7. And when you add that last rotation, what you've done, interesting. Interesting. So what you've, okay, so what I think it's happening, but I'm going to make another video on that with an example where I can see something else happening, because this example is too simple. I thought it was interesting because actually it was simple, but it might be a little bit too simple. Because for the first 2 iterations of the QFT, we don't see really any effect until we get at that point where it actually catches the negativity. It actually catches the negative phase, and it just rotates it 90 degrees. And when you do that, you're getting into this like it's 0.5 real 0.5 complex, 0.5 real 0.5 complex. What happens when you just give me a second? So I'll clear that for a second. Turn it into just 1 qubit, and I just want to try. So if we are like that, and then we're like that, then we're obviously, now when we add another Hadamard, as I said, we're like, so we're back to 1. if I now rotate a Z rotation, now I'm like, but here it's all, it went all here. Whereas here it's like, okay, because here we've got we're in a superposition, I guess. If I apply Hadamard to that, it spreads it over. Interesting. It spreads it over in the sense that it's then an equal superposition. I was just trying to, I don't know, because now, basically now when we apply the last Hadamard, uh, uh-huh, it kind of doesn't really matter in this case, because we are already, so we've already gotten the solution. That example is too simple, didn't work out. So stay tuned for next time. I'll try to find a better example. But so it's a combination of, okay, it's a combination of eliminating the superposition by applying the Hadamards, right? So the idea is you want to read out the pattern that's encoded in the superposition. So it seems like what this is really doing inside, like it's basically by, because it applies a Hadamard and to each of the qubits. So essentially, right? Essentially, if you would do that without the rotations, you would go back to your original state. Oh, I like that. I like that. I was at the end of the video. So essentially, if you would apply just the Hadamards, it just would come back to the original, to your original state. But by applying controlled rotations in between, you're basically tweaking this phase, you're tweaking this information, you're packing it all up, so it gives you what gives you the pattern. And I'm curious why there must be a reason why those particular angles are chosen. It's 90 degrees, right? 45 degrees, like 22.5 degrees. So each of those angles is kind of like half the previous one. So that also might have a there's a reason for that intuitively. Okay, cool. Stay tuned for more.